Okay, this is Dr. Erick Young, and his background is that he did his undergraduate work at UC Davis and then got his master's and PhD in astronomy from Stony Brook University. He was an astronomer at the University of Arizona for over 31 years. And he's currently the director of the SOFIA Science Center and works for the University Space Research Association out at NASA Ames. Dr. Young is a widely recognized authority on infrared astronomy. He has participated in virtually all of NASA's space infrared astronomy missions. He was responsible for developing the Spitzer Space Telescope's multiband imaging photometer and is directing construction of the IR detector arrays for the James Webb Space Telescope's near-IR camera. Dr. Young is the recipient of the George Van Biesbroek Prize for long-term achievements in astronomy by the American Astronomical Society and has had 5 NASA Group Achievement Awards. So, without further ado, let's turn the program over to Dr. Young. I hope I got that all right.
Okay, well, thank you for the very nice introduction. It's a pleasure to talk about SOFIA and some of the highlights and a little bit of the history of airborne infrared astronomy. So I think if we just go to slide number 2. When you work on an airborne observatory, you know it's actually pretty hard work, and you need to have a very good reason for going to all this trouble. And it's essentially presented on this chart right here. The long wavelength infrared is extremely important for understanding many aspects of cool objects in the universe, and it's going to be for things like planets, dust clouds, the main emission from galaxies is actually in far infrared. And all of those wavelengths between, say, 20 and 1,000 microns is going to be in a part that's essentially obscured by the water vapor in the Earth's atmosphere. And you can see that the transmission, even from a pretty good site, Mauna Kea, is not very good. And in fact, most of that region is 0. Since water vapor is the main absorber for this part of the spectrum, we want to go to a place where there's much less water vapor, and that means going up into the stratosphere. And so if we can fly into the stratosphere, we're above more than 99.9% of the precipitable water vapor in the Earth's atmosphere, and it becomes much more transparent, as you can see in the lower panel, where the transmission between 20 and 1,000 microns is more like 80%. So we'll go to slide 3. Just a little bit of history. NASA has been doing airborne astronomy for just about 50 years now. And the real pioneer was Frank Lowe at the University of Arizona, where he developed a system for the Learjet. And those observations were actually extremely important in planetary science, where he discovered that Jupiter was actually producing more total energy than could be accounted for by just the solar heating. And so there's an internal source of heat in Jupiter, and so that was one of the early discoveries of airborne astronomy. Next slide shows a picture of the Kuiper Airborne Observatory. And once you have gotten a taste of what's possible from the stratosphere, you always want to go to a bigger telescope, just like all astronomers want bigger telescopes. And so they went from a 12-inch telescope on the Learjet to a 36-inch telescope on a modified C-141 aircraft. And you can see the door just in front of the wing that has the 36-inch telescope. And the Kuiper was one of the really important astronomical facilities for about 20 years, from 1975 to 1995. And there were a whole range of instruments, and it included spectrometers, colorimeters, far-infrared imagers, and so it made many kinds of discoveries that were really important for making far-infrared astronomy possible. The reason it stopped flying in 1995 was to open up a little bit more budget so that we could complete and initiate SOFIA, the next observatory, which is shown in the next chart. So SOFIA is as big an airplane as we had available at the time. It's a highly modified 747 SP. And SP is a special performance airplane. And you can see that it's a little bit different than a standard 747 in that it's shorter. And that was actually very important in the performance, because a shorter airplane means much less weight, which means that you can carry more fuel and go higher because you are carrying less weight. And so these 747 SPs were initially designed for the long haul between, say, Los Angeles and Australia. And they flew for many years on those kinds of routes. The particular airplane that was on SOFIA was part of the Pan American fleet. It went to United and was rechristened the Clipper Lindbergh by Charles Lindbergh's son after it was handed over to SOFIA. The SOFIA project is a collaboration between NASA and the German Aerospace Center, DLR, and it flies up to 45,000 feet. And so that, if the weather conditions are typical, puts you above the troposphere and into the stratosphere, where things are extremely dry. We've got a full suite of imagers and spectrometers, and it's the only access to this part of the wavelength spectrum for the general astronomical community. The next slide shows a cutaway model of SOFIA, and there's some important things to point out here. First of all, you can see that the telescope is in the back of the airplane, and we have a pressure bulkhead, and I'll expand on the pressure bulkhead later on, but the main thing to draw from this picture right now is that it's the dividing line between the pressurized part of the airplane, which is the front, and the telescope, which is actually exposed to the stratosphere during operating conditions. And so it's at very low pressure, extremely dry, extremely cold. The temperature in the stratosphere where SOFIA operates is between minus 40 and minus 50 C. On the other side of the pressure bulkhead, we have the science instrument, which is mounted to the telescope. And then going more toward the front, we have crew stations for the instrument operators, for the telescope operators, for the mission control team. And then behind them, we have education stations for teachers who sometimes fly as part of the education and public outreach program on SOFIA. This is one of the unique aspects where we can allow non-NASA people to fly on the aircraft and actually take part in the exploration and thrill of the science so that they can share that with their students. It's a competitive process, and we've had a real good turnout there. Okay, the next slide shows some more detail of the telescope. And we have a spherical bearing that's mounted in the pressure bulkhead. And that center of the sphere is the exact balance of the telescope. And so that's actually an important part of the design, so that you can think of the telescope as a suspended mass of 10 tons, and the whole thing is 17 tons. But if it's suspended on something that has a center of mass at the center of a sphere, then if the airplane moves in yaw or roll or pitch, it's not going to actually move the telescope or apply any torques on the telescope. So at first order, it's a perfectly balanced telescope that tends to stay where it wants to anyhow. If you add onto that laser, gyros, and star trackers, then we end up with better than arc-second pointing. In fact, it's more like a half arc-second stability in our pointing. We also have active image motion compensators that ultimately provide something like a 2 arc-second point spread function. And so it's a pretty good performance for a telescope that's flying at 500 miles an hour. We have a wavelength coverage that goes all the way from the visible all the way into the millimeter range. And the telescope was built and is being maintained by a team from Germany. Okay, so going back in time, this is the infrared photometer that flew on the Learjet 50 years ago. And here we have just a single pixel germanium bolometer with a 2-liter liquid helium cryostat. And this is in the back, we're actually in the mid-chamber of the Learjet, and the astronomer, in this case would be Frank Lowe, would have to sit kind of scrunched in the same compartment with his helmet and mask on, so it was pretty tough to be an astronomer in those days. The next slide shows what I like to think of as essentially Moore's law applied to astronomical sensors, and you can see that the upper line is the growth of pixel sizes for visible light, and then near infrared, 2 micron range, and then far infrared detectors. And you can see that the far infrared is still way behind, but it's still following this exponential growth in capability, just because our sensors and the photolithography and other high-tech techniques are allowing us to make much more powerful instruments as time goes on. And so the next chart shows an example of the kind of instrumentation that we have on SOFIA now. So instead of a single pixel, we now have arrays of detectors that operate at the same far infrared wavelengths. And PFLS is one of our newer instruments. It was developed by Albert Krabbe at the University of Stuttgart. And it's an integral field spectrometer that operates at 2 far infrared wavelength bands. And it produces images that are 5 by 5 spatial pixels, but each pixel has its own spectrum. And it has 16 spectral elements, and so the number of pixels on a given array is 5 times 5 times 16. And we have a resolving power of 500 to 2,000, and it's obviously orders of magnitude more powerful than a single pixel spectrometer or a single pixel imager. The full instrument suite of SOFIA is shown on the next slide. And we have Forecast, which is a far infrared or a mid-infrared camera, and that operates from 5 to approximately 40 microns. GREAT is a heterodyne spectrometer, and GREAT provides extremely high spectral resolution, up to 10 to the 7 at 7 millimeter wavelengths. Flight cam is our near infrared camera. Here it's co-mounted with HIPPO, which is our visible light CCD occultation photometer. And the main use for these has been to do things like occultation observations over transit observations. FPLS was the instrument I described just a little while ago. And then XCs is our new very high resolution infrared spectrometer operating between 5 and 28 microns with resolving powers as high as 100,000. And then coming soon, if you click is a picture of Hawk Plus, which is our newest instrument, and it's in the process of being commissioned right now. It's a far infrared imager with 64 by 40 pixels, and it operates in very long wavelengths between 50 and 200 microns. One of the very exciting things about Hawk Plus, though, is the fact that it operates as a polarimeter and will allow us to use the far infrared polarimetry to help us measure magnetic fields. And that is turning out to be one of the really important topics in infrared astronomy right now. And the next slide shows a family portrait of Jupiter and the 4 moons. And this was the first light image of Hawk Plus. And this was just taken last April. Hawk will hopefully be flying again in a few weeks, and we'll finish the commissioning and make it available to the astronomical community. The next slide is just a chart which you can look at in a little bit more detail at your leisure. That just gives the summary of what the characteristics of the various SOFIA instruments are. The next slide shows what it looks like during a typical flight. And you can see that we have the back of the telescope right below the words telescope bulkhead. The instrument operators are sitting in that front row. Telescope operators are on the left of the picture. And then we have a mission director and a science flight planner as part of the flight. We often have as many as 25 people on a given flight, depending on how many visiting scientists and members of the science team are part. The next chart can advance to the next chart.
We have, but it looks like our video has frozen.
Uh-oh.
Deselect video and reselect it. But we are showing the flight path out over the Pacific now.
Oh, okay, great. All right, good. Yeah, and this is a typical flight path, and this is for a flight that's scheduled for later on this month. And you can see that we fly kind of a crazy path, and the reason for that is that SOFIA, if you think about it, is really like an alt-azimuth telescope. We have the ability to go up and down in elevation, but we only have a very limited range in tracking azimuth. And so the way to point the telescope azimuth is to point the airplane in the right direction. So if you wanted to look, for example, at a source that's in the southeast, then you have to fly southwest and so forth. And so the flight path is then determined by the mix of targets that you want to observe, when they're available, and it's kind of a difficult jigsaw puzzle to end up with efficient flight plans, because you have to throw in the priority of the sources scientifically, the availability in visibility space, and then finally you actually want to end up at your home base at the end of the flight and not waste a lot of fuel just flying a dead leg. And so fortunately our flight planners have gotten very good at this, and virtually all of the flight plans are completely packed with observations, and we effectively have very, very few dead legs these days.
Question?
Yes.
I see that most of the observations are out over the open ocean. Is there a reason for that, or is that to avoid the congested airspace over the continent, or are there other advantages to flying over the ocean?
This is a flight plan that was just driven by the sources that were needed to be observed. We often fly over the continental U.S.
Okay.
And it actually depends on the season and just the mix of targets that you have. But it is a lot easier to plan over the ocean because over the continental U.S. there are often restricted military areas that you have to avoid, and you have to sort of thread the needle between these restricted airspaces very often. And so the flight planners generally like to do it over the ocean. Okay, so let's see, the next chart shows a little bit of information about the deployment that we just finished. And are you advancing? It looks like it's frozen again.
It's frozen again. Yes, we're showing the deployment slide.
Okay, yeah, so we just returned from almost 7 weeks in New Zealand. This is Christchurch, New Zealand, where SOFIA went to the southern hemisphere and did observations of all kinds of different sources with 3 instruments. We also had a bit of an adventure during this deployment because we had a problem with the engine that required a replacement. And so on that top left picture you see another 747, and that's a 747 transport that we had to hire to carry a spare engine. And the guys replaced the engine on the tarmac at Christchurch, New Zealand. And so it's amazingly, we only lost a week's worth of flights because of that, and we're able to kick off 2 full flight series after that. And so the team was pretty spectacular when they did this. Okay, so the next slide shows an example of one of the observations that we did. And this was back in 2014, and we were able to take spectra of a supernova 2014J. And if you click once, you'll actually see the results. What this shows is the spectrum of the supernova, and the grayed out regions are actually parts of the spectrum which are completely obscured by the Earth's atmosphere. And what we see is a really strong feature in the 1.7, 1.8 micron band. That's actually a blend of 3 radioactive decay features, and they're infrared lines of a radioactive cobalt, and it's an important confirmation of the models. There are models of different epochs plotted right on top of the actual data that we have, and this is important because this particular type of supernova, which is a type 1A supernova, is used in the measuring the cosmic distance scale. The next slide shows a high-resolution map of Jupiter. This is high resolution in spectroscopy, where we're measuring 2 lines of molecular hydrogen, the S1 and the S0 line. And the difference between these 2 lines, in addition to being different transitions, is that the selection rules tell you whether or not the nuclei are lined up or anti-parallel. And by looking at this ratio of the ortho or para varieties of molecular hydrogen, that tells you, first of all, what temperature the material was formed at and what its thermal history was. And this gives us a measure that and says that the warm clouds are actually the result of material that's being welled up from deeper in the atmosphere. Next chart shows an observation of water in a star-forming region. And this is actually taking advantage of the extremely high spectral resolution of exes, so that even though the very few water vapor lines that are in the Earth's atmosphere are still going to be present in the spectrum, if you get high enough spectral resolution, you can get water vapor lines that are shifted. In this case, they're a little bit blue shifted relative to the Earth's line. And so you have on the lower panel the spectrum of AFGL 2591. Then also you have a spectrum of Vega, which is our standard star, which doesn't have any water vapor. And then if you take that ratio, you get the upper panel, which shows all these individual features, and they're all associated with various kinds of transitions of water. The next chart shows an observation of an outbursting protostar, and this is a star that just very recently became much brighter. The archetype of this class of stars is called FU Orionis, and it increased its brightness by 6 magnitudes in 1936, and it's been very bright since then. And people believe that the luminosity is partially driven, or largely driven, by the amount of accretion and matter that's falling into the star, since this is still an accreting star. And this proposal was a far infrared detection, one of the very few far infrared detections of an object that's in this state. There are only a handful of them known. And so this was a very successful observation. We were able to turn this around in less than a month. The next chart shows the power of the integral field spectrometer, PPLS. And here we're mapping the Orion Nebula in a number of different fine structure lines. And these are lines caused by elements in various fine structure states. And these lines turn out to be extremely important because in the energy balance of the interstellar medium, much of the cooling that's done by transitions is all in far infrared because the gas is very cold. And these are the common elements in the clouds. And so measuring the ratios of various oxygen and then a carbon plus, which is a singly ionized carbon, we can ascertain the total energy balance of the gas in the nebula. The next slide shows an example of forecast, which is the mid-infrared camera of the supernova in the galactic center. And this particular observation was fairly interesting because what it detected was gas associated with a supernova that went off tens of thousands of years ago. And the dust, well, the history of dust in supernova is an important question because in the early universe, we still need to form stars, and where did the dust in the early universe actually come from? And the only place to produce dust is actually in supernova for the first generation of stars. And that's because in the earliest part of the universe, The normal ways of making dust, such as mass ejection from high mass stars, is still hasn't happened yet because the stars have not had enough time to evolve. But here we're seeing that supernova can produce enough dust to possibly explain a large amount of the dust in the early universe. There was some question about whether that was actually going to be the case because when you have a supernova going off in a dense cloud, you get a reverse shock, which some models say completely destroys the dust. But here it shows that in this kind of environment, a significant amount of dust still remains. All right, next is a heterodyne observation of a planetary nebula. And this is the oxygen fine structure line at 63 microns. And it just shows you the power of the velocity resolution of the spectrometer on grate. Here we're able to get velocity resolved observations of this line. And what you see, first of all, is that there are lots of self-absorptions in the line. And if you looked at this line with a spectrometer that didn't have good enough spectral resolution, you'd get a completely mistaken understanding of what the amount of emission coming out of this planetary nebula would be in this line, because in reality a lot of it is being eaten out by material that's in between you and the planetary nebula. Okay, let's see. The next slide shows the power of the technology that we're producing. And this is just a map of a ionized region M17 with what's now a 14 pixel array. This is 7 beams on the sky, but 2 different polarizations. And so this upgrade of the great instrument to a multi-pixel array is much, much more powerful. And I'll show you a better example later on. And in fact, it's now described in the next slide. What we did was some demonstration observations. And what I wanted to do using a director's time was to provide an observation that could be used by the astronomical community that would be scientifically interesting, but also demonstrate the ability to use technology in a very powerful way. And so we made some observations in December of 2015, and we were able to use the multi-pixel great spectrometer to observe the Horsehead Nebula. And you may have heard of a space mission called Herschel, and that had a single pixel array that was an extremely powerful instrument. And in comparison, this same observation, which we did in 4 hours, probably would have taken something like 200 hours on Herschel. And the results are shown in the next slide. Here you see, as we scan through the overall line profile, and that's the integrated line profile over the full range of velocities, different parts of the nebula are interacting with the H2 region, which is on the right side, and you can determine what the velocity structure is in this carbon plus line. And the carbon plus line really maps out the interface between the hot ionizing gas and the dark cloud, which is to the left. So these data are available to anybody that wants to download them and analyze them. If you happen to have a Horsehead data in your back pocket, you can compare it with this. Okay, and then another science highlight is to measure the deuterium to hydrogen ratio on Mars with XEs. And again, we're taking advantage of the extremely high spectral resolution. And what people have known already was that there is a variation of deuterium to hydrogen ratio on Mars, depending on the topography on Mars. And so this is a continuing program on SOFIA to measure this D to H ratio. And what we find is that the disk integrated D to H ratio is actually about 4 to 5 times higher than what would have been expected based on, say, the Earth's oceans. And the explanation for that is that the deuterated water is heavier on Mars and is more likely to stay behind when water vapor gets sublimated from Mars. And this amount of deuterium indicates that vast amounts of water used to be on Mars but have sublimated. And it's actually consistent with the model that Mars once had oceans. And so that's interesting confirmation of what the models have already indicated. And then I'll close out with one final science example. And this example, it takes advantage of the mobility of SOFIA. Last year, the New Horizons mission had a spectacular flyby of Pluto. And we were fortunate enough to be in New Zealand about a month before the actual flyby event. And we're also fortunate enough to have the brightest, or an occultation by Pluto of the brightest star in this decade. And what we're trying to observe with an occultation is how the light of the background star gets blinked out by the atmosphere of Pluto. If it had no atmosphere, then it would be just a sudden drop in brightness and then a sudden reemergence of the star. But that's not what we're going to see. What we are going to see is a gradual decrease in the brightness, possible atmospheric refraction events, and that tells you a lot about what's going on. And so in this plot here, we're looking at the brightness of Jupiter, or the background star, and you can see that it's falling as it's getting occulted. And then right in the middle, there's a flash. It's called the central flash. And then the brightness of the background star is returning as Pluto moves away. In real time, this entire event lasted about 90 seconds. So, the gradual increase or decrease in brightness and the gradual increase in brightness indicates that Jupiter indeed does have an atmosphere, and by measuring the amount of, or the rate of decrease, we can determine some of the characteristics. And we were able to do this with the HIPPO focal plane imager and our mid-infrared or near-infrared flight cam instrument. So we had multi-wavelength observations, and that was extremely valuable because different atmospheric constituents will behave differently in an occultation event. The central flash is a special feature, and that requires you to be exactly at the center point of the observation. And that's caused by essentially refraction in the atmosphere focusing the light, so that if you're in exactly the right spot, you will get a momentary brightness called the central flash. And that's sort of the holy grail of these occultation observations. In order to hit the central flash, you had to be very, very close to the center line at the right time, and that meant that we were probably within 20 kilometers of the real perfect center line, and that required some fancy footwork right during the occultation, because to get within that kind of an accuracy, you actually have to know the position of Pluto and the star that it's occulting to within about 5 milliarc seconds. And so there were observations continuing even during the flight, and they were being analyzed from ground-based observations. And so we got our last update from an observatory at Flagstaff. The data were sent to MIT, where they were analyzed and sent to the team on the airplane. And they said that you have to go north about 200 kilometers to be in the right spot. So they stepped on the gas pedal and got and made it. And so that was quite spectacular. So the mobility of SOFIA was very valuable. So the last slide is my summary chart. It's a 2.7 meter telescope, which is quite large for something that flies, and provides the world astronomical community with access to wavelengths that are otherwise unavailable to the general community. We've got a full range of instrumentation, and we can go to distant locations to take advantage of special cases like occultations or go to the southern hemisphere. And we're operational. We're still in the process right now of selecting our fifth annual cycle of observing proposals, and they'll be announced in the beginning of October. But we're open for business and anxiously awaiting more proposals for future cycles. So the last slide is the summary chart. And there's actually one correction I should make. It's actually HTTPS instead of HTTP, but otherwise that's the right address. Thank you.
Okay, thank you. Questions?
Yeah, I have one question. Dr. Young, would you take a moment just to tell me again about that central flash? How is that created? What is it?
Yes, if you have a refracting atmosphere, then the light, if you're perfectly centered on this, will bend around and tend to be focused more in the middle. And so you're getting a symmetrical focusing of the light.
Yes, that makes sense. Thank you.
You seem to be frozen again.
I have a question.
Question in the back, or?
Yeah. How is the time allocated between the Germans and the Americans? Is that negotiated a long way in advance, or is that? I imagine it's quite a complicated process.
Well, it's actually not that complicated. It was agreed when the project was first set up, and it just essentially depends on the financial contribution of the different partners. And early on, and this was back in 1997, I believe, they agreed that Germany would provide 20% of the support for SOFIA. NASA would provide 80%, and so the time is allocated 80-20. We don't force that year by year, but we keep track of it to make sure that on the average it works out to be 80-20, and it's been actually pretty close.
So they have the Germans have a separate a process for finding, for accepting proposals, or is it all one process?
They have a separate time allocation committee. And so in this last year, we were offering something like 500 hours on the US side and 80 hours on the German side. And so it works out, first of all, in how we solicit proposals. In terms of the actual call for proposals, the text is virtually identical for the two calls for proposals, so the scientific criteria for the observations are the same. But we do have separate committees that select the investigations.
And I had one other question about the instrument. You only fly one instrument at a time, or can you have several instruments?
Just one at a time. It takes a couple of days actually to do a complete instrument swap.
Yeah, okay, good.
How many flights have you taken?
About 10. The observatory is up to, I think, 280 flights already, but I've personally only taken about 10.
Along with the instrument, the facility instruments, has SOFIA ever hosted guest instruments? I assume the instruments have to be pretty much designed specifically for the instrument bench there. So I assume you do not have a visitor bench or visitor program for instruments?
That's correct. The instruments are very, very specific for SOFIA because the interfaces are complicated, and not only that, you have to satisfy airworthiness requirements, and so there are essentially this giant, thick book of interface requirements that you have to satisfy. That being said, though, we have several classes of instruments. One is a facility instrument, which is actually operated by the observatory, but we have principal investigator class instruments, and the two examples that are prominent right now are GREAT, the German heterodyne instrument, and EXIS, the very high spectral resolution mid-infrared spectrometer, and both of those are operated by separate instrument teams, and so they in fact have a bit more freedom to make modifications to their instrument and keep them more on the cutting edge of technology.
Another question, how long is a typical flight?
It's about 10 hours. We spend 1 hour on the flight, half an hour getting to altitude, about 9 hours actually doing observations, and then a half hour in descent. And during that period of time, we try to climb as high as possible at a given moment. And how high we can go is basically determined by the weight of the airplane. So as we fly through the night and we burn off fuel, then the plane becomes lighter. And so we often start off at 39,000 feet and then go to 41,000 feet and then 43,000 feet. And the higher the better in terms of water vapor.
So is the telescope pre-cooled before the shutter, whatever you call it, beside the plane is opened, or does it take a cool down period once you go open?
Well, we had considered doing a pre-cool, and that would gain us about half an hour. But that's actually all the time it actually takes. And when we're doing our initial telescope setups, finding our first star, doing alignments, that typically takes 20 to 30 minutes. And during that period of time, the telescope reaches equilibrium temperature, and it's actually fine at that point. So we decided not to have this pre-cool system because it would have required a lot of safety considerations because it would involve pumping thousands of liters of liquid nitrogen into the cavity, and so that was just too much to consider for small gains.
Does the telescope care about minus 50 C?
No, it doesn't.
Could it go colder? I mean, is there an operating limit in terms of minimum temperature?
Well, I don't know how cold it could actually get. There is a bearing, the spherical bearing that supports the telescope, and it will operate until the oil starts too cold. And I actually don't know the limit for that temperature. But on the other side of the bulkhead, you also have something that's room temperature, and so there's going to be temperature gradients there, which will ultimately cause problems. The telescope itself is normally at about minus 30. The air around it is at minus 50, but there's actually an aerodynamic effect that when you're flying through the air and you have to slow the air down and it reaches into the chamber, it actually ends up at about minus 30 instead of the actual stratospheric temperature of minus 50. But in any event, the telescope itself is designed to operate very thermally stably because it's first of all, the primary mirror is made out of zero viewer, which is a ceramic material that has almost zero coefficient of thermal expansion. The secondary mirror is silicon carbide, and the tertiary mirror is fused silicon. So all of these are effectively zero coefficient materials. And, so it's pretty thermally stable to begin with.
Very good, thanks.
I noticed on the diagram of the aircraft, there were some seats at the very front on the right-hand side that didn't have an indication of who sat there. Is that
Teachers, like you.
Yeah, those are
just general?
first-class seats, and we have visiting astronomers that can sit there, or anybody else that wants to ride there. A lot of times, you are supporting an observation that doesn't take a whole flight. For example, if you're a guest investigator, we don't allocate flights by entire flights. We allocate them flight leg by flight leg, or hour by hour, and so your own observation might only be a fraction of a flight, and so you can sit there and read the Astrophysical Journal while you're waiting for your flight.
Standby seats.
Yeah.
Would you ask him if we can put this on the internet?
Oh, that's true. We have been recording the talk, and would it be okay if we put the talk on our Big Bear Valley Astronomical Society Facebook page?
No problem.
Okay, great, thank you. There are, of course, always people that can't make it to the meeting, and we've only had one speaker thus far that couldn't do it, and that's because he had some data that he forgot to ask the other people about first. So. Anybody else have questions?
You mentioned director's time. How much discretionary time is left available?
I get 7% of the time. But I end up giving almost all of that to the astronomical community because most of the director's time is used for a reserve for things like if a supernova goes off, then you have to be able to schedule that with some time, and so you do that with director's time. And that in fact was one of the big uses of the director's time. And then the Horsehead Nebula was another use of director's time where I just dumped the data on the astronomical community as a way of demonstrating how SOFIA could improve their ability to understand Photon's dissociation regions.
So you try to keep a little bit of time in your back pocket for targets of opportunity then?
Exactly.
Okay, any other questions? Well, if not, then let's thank Dr. Young again, and then we can let him get on with his evening. Again, thank you very much, and we really appreciate having you tell us about SOFIA.
So it was my pleasure.
Thank you.
Okay, good night.
Okay, good night.